using the high luminosity projector with the lens is mostly not glass, is probably, so it will be very heat sensitive. So don't put anything in front of the lens. And if you want to hide your information, then basically that you either switch it from using the physical switch, or you can use the extended of your window. So in this case, that nobody will see your PowerPoint. Okay, and then so the stage regulation is so to begin with, the opponent charge the reporter for a problem. The time is 1 minute. And the second is the reporter accept or reject the challenge, also 1 minute. And the preparation of the reporter, once the reporter accepts the challenge, then the time is 5 minutes. And then the reporter have 12 minutes to present his study. And after that, the opponent have 2 minutes to question the reporter and get some brief answers from the reporter. The time is 2 minutes. And after that, the opponent has 3 minutes to prepare your challenge. And then after that, the opponent and the reporter have 40 minutes to discuss. After the discussion, the opponent has 1 minute to summarize. And then in the next 3 minutes, the reviewer can question to the reporter, and the opponent have answers to the questions. And after that, the reviewer have 2 minutes to prepare for his review. Then the next 4 minutes, the reviewer will review the entire process for the presentation and discussion. And the reporter have, after review, has 2 minutes to conclude. And finally, we have 5 minutes for the jury to question. And basically, the questions are either the score from the question is either 0 or negative. So, so we will try to be fair to ask questions to all teams. So that's basically the question for this fight. So let's start with the first challenge from the opponent.
Number 6. Number 6.
Okay, ask to the reporter. So clock is ready. We start right now. 时间不对是不是？
那连不上，现在连不上。
Oh, okay.
录影机有点问题。
Just a second, there is some technical issues.
Oh,
是都没有网络是不是？
别针也是。
对。
哦。嗯。
我
所以不到为什么？所以你们在用，因为用卡可换，你们没办法。
你们有没有那个网络可以先让他试一下？
接不了，因为他就是接手术没看我搞不清楚。
其他的都不行吗？ 机可以，但是它现在没有网络啊，所以它没有那 class 没办法。
那个送煤带那个问题，那个我们是不是还是要了解一下？我叫他再拿个 U B 来试试看。
现在是网络问题还是电脑问题？这个是网络问题。
你有没有带电脑？这样带。
对啊，那有没有那个？
刚才那边的学员他是用他的 notebook 来测试 OK 的，可是我们的送煤带不行。
那我们用自己的那个也不行。
除非换电脑，直接换成电脑。
但我还需要去哪？因为它好像是网络问题，就是它送给派的设定问题，所以
也有可能啊，因为它设定的话都是就你在设定。
你是都没有不用电脑？
是怎样用自己的电脑？
好，进
因为我们在challenge，so the opponent you have 1 minute to challenge the reporter.
New report number 6.
Number 6, power number 6. So you challenge, you accept it?
Accept the challenge.
Okay, the problem number 6 is accepted. So the reporter, you have 5 minutes to prepare. And in the meantime, all 3 teams, please write down the name of your representative. 等一下在上面写那个 accepted province。现在已经在5分钟了，对，现在就是那个看一眼剩的就是5分钟，他准备我到，他就要报告了。这里面只有你一个工作人员吗？那还有一个是谁？ Okay, write down problem 6, accepted. So if you are ready, then you can let me know. But you have up to 5 minutes. Yeah. 他要开始了，是不是？Okay. Wait until they are ready, then we set it. Start.
I'm the reporter from. Hello everyone, I'm the reporter Ethan Xu from Team Excellent for problem number 6, magnetic mechanical oscillator. First, we can look at the problem statement. Secure lower ends of two identically springs to a non-magnetic base and attach magnets to the upper end such that they will recoil and are free to move. And we need to investigate how the movement of the springs depends on relevant parameters. As the experimental setup, we set the two identical springs and a pair of the recoil magnets to do the phenomena. And for the analysis, we use tracker to track the trajectory of the motion. And for the Python, we do the Fourier transfer and the numerical modeling for comparison with our experiment. And to investigate about such a system, we are first going to find the relationship between the single oscillator. So first, we form a force displacement measurement so we can infer the effective mass M in this system. And after we get and we can also get the elastic coefficient about the mass M. And for the preliminary observations, the oscillations amplitude will dim away as the time evolves, and the oscillations will transfer from one magnet to the another. So then we start to categorizing a single.
Let me stop. Just so for the reporter that you can take off your mask. Yeah. So stop the counting.
And for the categorizing a single oscillation, it can be modeled as a single magnet plus a leaf spring system. And as a damping harmonic oscillation, we can write the equation of motion for the single oscillations. And in our cases, which is the underdamping, on the graph we can show the underdamping, and we can write the function for the fitting result. And so we track the trajectory of the single oscillations, and we fit the experiment trajectory to find the oscillation frequencies, and we also find the gamma, which is our coupling term, which is our damping term. So here's the fitting result. As to theoretically modeling it as a general coupling oscillators, we can first consider two identical oscillators coupled by a string. So we can written the two equations here. And when we add the equation together, we can find the symmetric mode frequencies in this system. And we minus the equation 1 minus the equation 2, we can find the anti-symmetric mode frequencies. And to introduce about the two different normal mode frequencies, we can see that the symmetric mode frequencies only depends on the mass, effective mass, and the effective elastic coefficient. And for the anti-symmetrical frequencies, it depends on the effective mass, elastic coefficient, and also the coupling terms. And to find the fitting in the coupling oscillators, the general solutions are linear combinations of both normal modes, as the equation we shows. And when the coupling is weak, which means the two frequencies is similar to each other, we can find the bit frequencies, which is the differences between the two different frequencies. And we are going to find the relationship between the magnetic force and the spring coupling. Since there is some differences, such as the spring force is a completely linear system, but for the magnetic force, it is a nonlinear system for the relationship with the distance. And the magnetic force ends bidirectional, which means it only attracts and repels to each other. So according to reference 1 and 2, the force between the magnets can be approximated as the equation here. Under the circumstance, which is the distance of the two magnets is larger than the length of the magnets, we can simplify the equation here. And for the formula from the reference, we can show that in this distance, that the magnetic can be written as the equation here. So we experimentally obtain the force distance curve and fit it in the simplified formula. And for the formula, we are going to find the magnetic coupling strength and the regularization constant factor, which is epsilon. And so we approach our magnet to the magnets on the springs, and so we can find the induced displacement and the magnetic distance. And to use the previous fitting result that we just introduced, we can change our graph into effective mass force to the magnetic distance. And then we can do our fitting curve for the previous equation, and we can get the result here, which is our constant factor and the coupling strength. So after our previous discussion, we can write the equation of motion for our system. in this equation, we can resolve it into three parts, such as spring force, damping terms, and the magnetic couplings. So we can resolve it into Python. And so when we plug the equation into Python, we can find the trajectory of our calculations. So we use the previous experimental result and we plug into our equation of motion, we can find the trajectory theoretically. And the right side is the experimental result. So to compare the two results, we can see that our theoretical model is great agreement with our experimental result. And here's the first experiment is about the initial displacement. Since nonlinear oscillations often depends on the initial displacement, we want to check this is not the case in our experiment, since it doesn't mention in our equation of motion. And here's the first experiment about we place the initial displacement for 1.1 centimeters. That we can see there the coupling can be easily observed. And for 1.5 centimeters, we can see that the frequency doesn't change, which is back in our theory, and the amplitude have been larger. And here's the result for 2.2 centimeters, the amplitude got larger and the frequency doesn't change. And for the result about the initial displacement, we can see that both of the normal mode frequency doesn't change when we add different initial displacement, which is back to our theoretical model. And here's the second experiment that we change the coupling strength by changing the different numbers of magnets, and we keep the mass of the upper ends is same, which we just mentioned in our equation of motion. And here's the result for one magnet. We can see the two different frequencies can be observed. And here's the result for two magnets. We can see the symmetry mode didn't change. It's only changed in the anti-symmetry mode. And here's the result for three magnets and four magnets. We can find that the symmetry mode won't change over the time, with getting more magnets, since we mentioned it only depends on the effective mass m and effective elastic coefficient. And here, as a result, we can see if we increase the numbers of the magnet, the anti-symmetry mode will change, but the symmetric mode didn't change when we add different parameters. And here's the result for coupling, that we change the coupling strength by changing the initial distance that we just mentioned in our equation of motion. And here's the result for 2.6 centimeters. We can observe the two different frequencies, which is the symmetry mode and anti-symmetry mode. And here's the result for 2.6 centimeters, that the anti-symmetry mode have been larger, but the symmetric mode is remain. And here's the result for 2 centimeters. Especially, we are discussing about the 1.6 centimeters that it have the same thread about that the anti-symmetry mode got larger, but the coupling can be easily observed, which means that the two different frequencies is not similar. That we just mentioned, to find the beating, there must be similar, the frequencies. And as a result, we can see when we add the more distance about the two magnets, the frequencies of the anti-symmetry frequencies will decrease. And here's a discussion about the modeling as a coupling oscillator. So to simplify the theoretical model, we approximate the magnet coupling with a spring coupling. So by Taylor expanding the magnetic force, we can find the kappa prime, which is our magnetic coupling strength. And so to modeling as a general couple oscillators, we can replace the magnet as the spring in the middle part. Then the elastic coefficient for the middle part of the spring can be written as the equation that we just mentioned. So as a tentative physics picture, if K1 and K2 is much larger than kappa prime, will mainly be compressed and tries to repel M1. So the magnetics will act like the spring that will only compress. And here's the discovery of the normal modes that we just mentioned. So we solve the full equation of motion without linearized coupling. So we can pick the initial conditions and we discover the two situations, which is the symmetry mode and anti-symmetry mode. So here's the result for the numerically modeling. And here's the animations and the video about the symmetry mode and anti-symmetry mode. So the two motion behave like the two independent oscillations, which means there's no beating behaving in this system. So here's the result for the symmetric mode. And as a result, we can see there's only appears the one single frequencies in our fast Fourier transformations graph. And here's the result for anti-symmetry mode, that there's also have one single frequencies can be observed, but it is larger than the frequencies of the symmetric mode. And here's the conclusion about my presentation. So for the phenomena, as a video and both the trajectory, we can find the oscillations will transfer from one magnet to the another, and the beating in the trajectory can easily be observed. And so we developed the theoretical model to describe the motion coupled oscillator. So by experimentally categorize the oscillators and magnet strength, we obtain the volume for the equation of motion for the numerical modeling. So as a result of our fitting, we can plug it into Python. So we found the good agreement between our theoretical model and the experiment. And for the first experiment about the initial distance, we can find the initial distance only affect the amplitude of the oscillation, but not affect the frequencies. And by changing the numbers of magnets, when we place more magnets, the anti-symmetric frequencies will increase, but the symmetric mode didn't change. And when we place more distance of the magnets, the anti-symmetric mode will decrease. But when under a circumstance that the two magnets is close enough that the coupling can be easily observed. And inspired by our experimental observation, we theoretically developed a simple couple oscillator model to describe the phenomenon. So we changed the effective spring coupling as a couple prime. And as a result about the symmetric mode, motivated by the simple model, we further explore the normal modes of the oscillator both experimentally and numerically. So here's a result for the symmetric mode that is only depends on the effective mass m and the effective elastic coefficient. And here's the animations and the experiment video. And as the anti-symmetric mode, this will be bigger than the symmetric mode, and it will also depends on the coupling strength, which is a kappa term. And here's the animation about symmetric mode and anti-symmetric mode. Here's all of my presentation. Thank you for listening.
Okay. Now, the opponent, you have 2 minutes to question the reporter. So the representative can take off your mask during the discussion.
Do you get the magnetic flux?
Since a magnetic flux is one of the behavior about the magnet, we measure the magnetic force on our lift string to find the effective magnetic force. Since I think the magnetic, if we simply find the magnetic force, it can't be effect on our system since it's a bending system.
Do you make sure the force applied by your hand is the same?
Yes, because that we place rulers on the back part to make sure that this initial distance that we provide is the same.
What's the material of the stick? Just
The material of the stick, we provide a lift string to do our experimental experiment setup. And so to make sure that can be simplified as a lift string, we have measured the elastic coefficient, effective elastic coefficient, since it's a kind of lift spring. So the bending will be the main reason that cause the spring gets the initial distance.
so is the two of the magnetic the same?
Could you ask your question?
The two of the magnetic is the same.
Yes, we make sure the two magnets is identical. Since it is mentioned in our proper statement, I think this is very necessary.
So do you get the magnetic force?
Yes, we find the magnetic force on our lift spring to make sure it is effective magnetic force.
All of my questions.
Okay. Yeah. So in the next stage, you have 3 minutes to prepare. Okay, opponent, you have the up to 4 minutes to present and then followed by a discussion with the reporter.
My name is Shin Mo, and I'm from PF1. This is the problem statement of this, and they focus on the movement of the spring's relevant parameters. And their theory is characterized a single oscillator and coupled oscillator, normal model in coupled oscillator, and betting in coupled. The setup is magnetic and spring coupling, and parameters is initial displacement. And the motion behave independent. And I think their PPT is clear and their state is also very clear. And in the 2-minute discussion, this is the question I asked. Okay, so I have some questions to ask.
Okay.
How do you fix the stick?
How do I fix the stick? So I place it on a non-magnetic base to make sure that they can connect to each other, but they won't affect each other when they are single oscillations, in a single oscillation.
So what's the material is the base?
The material of the base, we place a wooden material to make sure that the base can be static.
So what's the force you think affect this system?
So the first force is that when we pull the initial displacement for the spring, we provided the spring force. And between the two magnets, we will provide a magnetic force.
Well, is your magnet is at in the same side of the stick between them?
So we have the spring. We have make sure that the magnet will be in front of the spring, that to make sure the magnetic force will be well measured.
So it will be held. The stick will not be
Bending, means bending. So the distance of the magnet, we make sure that the magnetic force won't make the spring bending. which we can see in our observation videos, that the distance for the two springs can make sure the magnet won't initially provide a displacement for the magnet.
So how do you measure the magnetic force?
So the method that we measure the magnetic force, first we approach our magnet to the magnetic on the springs, and so we can measure the bending that we make, the induced displacement that we make the springs bending. Is that correct? And we have measured our effective elastic coefficient previously, so we can change the induced displacement into the magnetic force. That is the method that we measure the effective magnetic force on this spring.
And do you think the stick can be used as a spring?
Yes. Since it is a leaf spring, so we, under some circumstance, which is a small amplitude, we can simplify it as a spring. To make sure it can be measured as a spring, we measure the effective elastic coefficient, and we can find this is a linear relationship between the displacement and the spring displacement. So we can make sure, maybe not make sure, so we can think it as the effective springs in our cases that we have measured. Since it's this spring, we have measured it.
So, what the motion do you think if you just have the one stick?
If in our cases, if we only provided one stick, so there is no coupling and it will acting as a single oscillations that in our categorize. So we can use the single oscillations to find our damping terms and frequencies that if there is no coupling in the system.
And what have you considered about the magnetic coupling coefficient?
Coefficient? Yes. Do you mean the kappa prime that in our discussion?
Yes.
The kappa prime in our discussion, first, we think it can be, so expand our magnetic force into a small under some circumstance, it can be simplified as the equation that we provide, that's from the reference. So that we show the graph of the reference that the curve will fit in some small circumstance to make sure the formula of the magnetic force can be correctly measured.
Do you consider the size of the magnetic?
The size of magnet? Yes. And for our formula, we have considered the length of the mass. We have considered the length of the magnet and the radius of the magnet in my formula. And then to find the actually magnetic force, we can simplify this as a term called kappa on our equation. Then we can measure the use the fitting to find the kappa that simplifies as our magnetic coupling string.
Do you measure the magnetic field?
The magnetic field between the two magnets?
Yes.
I think the magnetic field is one of the characteristics between the magnets. But in our cases, we only measure the magnetic force to do the coupling to fit in our equation of motion to make sure that the magnetic coupling term is correct.
Please turn to page 60. So, what is this?
This is the error bar of my experiment data.
So, why is the error bar get smaller?
It is a quite interesting question because for our experiment that we know when the magnet is so closer to each other, the force will increase. Is that correct? And when the distance is small enough, that the measurement will be hard to be in the same volume for the magnetic force. So we do our experiment for quite 10 times to make sure that the error bar can be correct. So we can see in this graph, when the distance is more larger, that the error bar will be smaller. And when we increase when we make the distance of the magnet get smaller, the error bar will increase.
What include your damping coefficient?
In our damping coefficient, we can consider some, such as the connecting point of the materials that make the system damping, and also the energy increase in the damping. So, to find the reasons that make the energy increase is very hard. So we use the fitting to fit the damping terms to make sure the damping coefficient can use in our experimental for our numerical simulations.
Please turn to page 36. You can see the highest is turn to the down of the wave. So what do you explain this?
This is the reasons of the coupling system, but in this case, that the distance of the magnet is closer enough to each other. It will acting like the like the normal mode that we just provide. So it will oscillations like quite independently, but they still have a coupling effect on the system.
Sure the one ruler is simple harmonic.
Maybe not quite a simple harmonic. Harmonic, I will say it as a damping harmonic oscillator. So we can look at the graph here. I can share some interesting things in this graph, such as why when the distance of the two magnets is quite close, when we close one side of the magnet, the other side maybe when the initial distance setting as the small distance, the sum of the bending will be considered in this system, and so we close one of the side. The bending part in another side of the spring will have restored in the balance point. So when we have the motion in this circumstance, which is 1.6 centimeters, it will act in like a symmetric mode that we just introduced. So we can see the anti-symmetric mode has been appeared, but the amplitude of the anti-symmetric mode has been quite small.
You measure the force of the magnet.
So, do you talk about the formula for the fitting of our magnetic force and the distance? Yes. In this page, we can see that the coefficient here, we can simplify it as a kappa. So, in our fitting curve, we will use the kappa here to do the, so we can know that the force is a function of the distance.
So what is this number?
This number is in the formula of our reference to And to make sure that the formula can fit to our result, we can see at the graph here, which is come from the reference down part, that we can see in some circumstance, in some distance, in the initial distance, the magnet force can fit the curve of this formula. So we make sure the distance can be fitting in those areas of the graph.
Okay, time's up. So, opponent, you have 1 minute to summarize the discussion.
We talked about a lot of things, and they help me and they answer some of my questions perfectly. And this is all of my conclusion.
Okay. And then the reviewer, you have 3 minutes to question both the reporter and the opponent.
Can I go by math?
Yes.
So, you pull the ruler and you make it oscillate.
Yes.
And have you considered the mass of the magnet?
Oh, this is quite interesting. And in our system, we think not only the mass of the magnet will affect the result, we think that the mass of the spring will also affect the result. So we measure the effective mass M, not only the mass of the magnet, to do the fitting and the numerical model.
Okay. What do you think about this question?
My thing is like what you think.
Okay. So, have you tested the length of the ruler different than?
I think the length of the ruler is also an important parameter in a bending situation. But in our situation, by changing the length of the ruler, it will also change the mass, effective mass. So in our cases, we also only discussed about the coupling strength. So by changing, I think the parameters that the reviewer provides is also an important part. But if we change the length of the lip string, we will have changed 2 parameters in the same time.
Okay. And you, what do you think?
I think if you change the length of the ruler, there is some of confusion will change, and it may have to experience more.
Have you tested different magnets?
Different magnets.
Yeah.
So we change the amount of the magnet by changing a different magnetic strength. Is that what you're asking? Or changing the shape of the magnet?
The material.
The material of the magnet. I think this is also a quite important part for the changing the magnetic coupling strength. But in our situation, to make sure the coupling strength and the effective mass can in the same range, we only use one type of magnet and we change different amount and the initial distance.
And you have a picture that 2 volts and it oscillates here.
Yes, about
And
introduce the normal mode.
is it close to your device?
So
your experimental device?
We have discussed since the animations about the normal mode can be completely fit to our experimental result. So we discuss it in our discussion 2, which we provided a normal mode system to make sure that the middle part of the magnet can be similar to the.
What do you think? How much do you understand about phase effect?
I think just a little.
Okay, time is up. The reviewer have 2 minutes to prepare. Okay, time is up. So you have problem with your.
Yeah, I just get it in, but it can't be shown.
Okay, stop the time. But next time, better check before the file. Okay, try again. Unplug your cable and then try. Okay, cut. Just a second. Okay, start counting.
Okay, reviewer, I'm going to review the number 6 magnetic mechanical oscillator. Here's a problem statement. It says secure the lower ends of two identical leaf springs to a non-magnetic base and attach magnets to the upper end such that they repel and are free to move. And then investigate how the movement of the springs depends on relevant parameters. Here's the performance of a reporter. The theory they have full explanation of the phenomenon, and it's the experiment part. They discuss how different parameters influence the results. And conclusion, they connect the theory and their experience quite well. And they have good time management and full explanation of the phenomenon and well understanding to the experimental device. However, did not discuss different materials of the ruler. As for the performance of opponents, they have well understanding at the problem and well discussion with the reporters. However, they have poor time management and did not totally understand what the reporter meant. And discussion point, they first discuss how to measure magnetic force, and the reporter replies they use their schematic diagram of experimental device to explain it. I think it's quite clear explanation of how to measure magnetic force. And as for the size of the magnetic, the reporter said that explained it by their formula. And however, I think the reporter can also explain it by their experimental data, so the opponent can understand it more easily. And then they also talk about why their coupling strength data act like they are peaks and they're getting smaller and smaller. A reporter said that they explain why the peaks appear, and I think it's good to explain it with their data, but perhaps they can also use it by their media, since they have media. So, and if you take it with the media, the opponent will understand it more easily. And there's a point missed. They did not discuss the length of the ruler, and I think it might also influence the movement of the oscillator, and the volume and the mass of the magnet is also a parameter that is worth discussing. And this is the end of my review on this. Thank you for listening.
Okay, and the reporter, you have 2 minutes to make your concluding remark.
Since both of the reviewer and the opponents point that I can be more improvement in future. And first, as my concluding remarks, as my presentations highlight, we numerically the theoretical models for the simulation model, and we figure out and categorize the magnetic in this system by measuring the force between the magnets. And we do the experiment that prove the parameters that affect and that don't affect, which is the effect result by changing the coupling strength. But the don't affect result is that the initial displacement, which we didn't mention in our equation of motion. And we feed the experiment result to the theoretical model by using a Python to do the calculations of our equation of motion. And finally, develop a simple spring-coupled oscillator to describe the phenomenon, and we also lead the concept about the normal mode. For the two types of normal mode, there is symmetric mode and anti-symmetric mode. And the fixing point that we can do some measurement for the other characteristic of the magnet to find out if there are some other relationship in the system. Since the opponent mentioned, I can measure the magnetic field strength, and we can also measure the flux of the magnet, and change the material of the magnet to find out if our theory can fit in other situations. Since we just mentioned the size of the magnet, didn't mention about the materials of the magnet. And for some improvement, the reviewer mentioned some parameters. I think there is also important, such as the length of the lead string and the mass of the volume of the magnet. But by changing the length of the lead string, we need to do the fitting for the single oscillations again to find another effective mass and another effective length. Again, I'm saying for the reviewer and the opponents some points for me to improve.
Okay. We have 5 minutes for juries to ask questions.
Question. Yes, if you go to the slide 36 about the complement. Okay, I ask the question first.
Okay.
Yeah. No matter you change the size of the magnet or changing the number of magnet, the effective mass should be changed. Why the power spectrum doesn't change for the symmetry mode? Can you explain that?
Could you present your
I mean,
question?
no matter you change the number of magnet or the size of the magnet, the effective mass should be changed.
Yes, it should be.
But for your according to a power spectrum, the speakers of the symmetry mode doesn't change. Can you explain
Yeah,
that?
I think this is a very important point. And in our experiment 2, that we have shown some picture that we control the mass on the upper ends by using some other materials to make sure the effective mass won't change. And we only change the magnetic coupling string by changing the kappa.
How can you fix that? Because the distribution or the mass distribution might not be the same. I mean, how can you fix the effective mass of the same? Because the mass distribution might not be the same. Even the total mass is the same, but the distribution is not.
So, you mean that when we change the different things, although we remains the total mass is same, the effective mass will also change. I think it is quite a point to be discussed, but in our result of the comparison with different parameters, you can see that the symmetric mode have changed little, but since I think the effective mass won't change a lot. But this is also quite an important question. That's why is the symmetric mode will change little in this situation.
The same question is also asked for any other input, or do you have any idea about this for the component?
I think the mass will not include the system. In my opinion.
Then how about the reviewer?
Can you repeat the problem again?
I mean, it's the same question, and how about your idea about
The mass of the magnet? I think it may also influence the magnet. Because perhaps the force is different. The gravity, the force, it may also influence the device, how the device works.
Okay. Any other questions?
You try to determine the effective mass, but your system actually is, I mean, the moment of inertia, should it enter the picture? But it's more realistically, it should be determination of moment of inertia and the constant for torque.
So do you think that since this is quite of the motion of the moment of the inertia should be considered in our calculation?
When you have torque,
I know
it's not a
they're
linear.
completely linear, right? But in our measurement, we make sure that the oscillations will make
The amplitude is small enough.
Yes, small enough. Then we can simplify.
So that has to do with your length too. Length of
the length of the spring.
leaf
Yes.
speed.
So the opponent asked the question by changing the length of the spring might also make, like the professor said, to consider the moment inertia in our experiment. When we make the length of the spring get smaller, that the amplitude to the length of the spring will be larger.
So, reviewer, do you agree with the reporter's remark?
Well, I think the lens would also have a big influence to the experimental device.
He said the amplitude.
If you put it at different parts of the ruler, you put it with different forces, and they will influence the results of this experiment, in my opinion.
Okay, time is up. And so let's prepare the scores. Okay, so if you are ready for the reporter score, then we will show. Okay, okay, let's show the reporter score, and I can see it. So it's 88878. Okay, and then let's show the score for the opponent. Okay, it's 66445. 66445. Okay, and then finally let's show the score of the reviewer. Okay, 77867. Okay, so we can have a short break of 10 minutes, right?
Yes.
Okay, and so before the break, please switch your positions and try the computer first, because you might use different computer, and so please check if your computer can show up on the screen properly. The opponent, you have 1 minute to challenge the reporter.
Number 4. Okay.
Problem number 4. So you accept? Okay, so the problem number 4 is accepted. And then the reporter, you have 5 minutes to prepare. 哎，那时间呢？好，5分钟了，都没有在看的时间。
找到密码书。
上面那个，就下面的。
等一下吧。哪一个？哎，为啥？ 哪个？这个够不吗？这个吗？
对对对。
这样是这个吗
5分钟。
哦，他们要第四题。
他们第4题。
你就跳一直跳到5分钟的。
好，他们接受。
接受了，对。
对。
看下面。
那要写那个 problem number 4要写在黑板上。
要。等一下，那是谁？
大家。
没有这个人吗？女朋友是不是？
对啊，你名字在上面。
女朋友，我看一下。女朋友是你是乌总。
没有，他队友。那原来队友是哪一位？
原来是。
哦。
对啊，对对，这个啊，这个人在这边，王定轩啊。
他那个上面没更新到。
他是有没有 update 到？
新的那个好像有。
有啊，新的有啊，他是 update 的，所以如果你那边弄不出来就没关系，他写在黑板上。 Ready?
I'm ready.
Okay, start counting.
Yes, honorable judges, engineers, and opponents. I'm going to share from Team PF1. And the topic I'm going to present today is number 4, colored line. And this is an outline. Problem statement, comparison, terms definition, experiment, method, device. And here are our experiments, and the discussion and conclusion, and the problem statement. When this is united with the large angles of incidence, a clear green line can be observed. The color varies upon slightly changing the angle of the disc, and our main focus is large angles and green line. And for our experiment, we put our disc in the dark room, and we fix our incidence size, height, and position, and move our observation point up and down to find the green line, just like a picture there. But in our experiment, it won't be really like this, because the background should be black, and we use image J to see the lambda of our green line. And this picture is to talk about the wave path differences, and double flight isn't about this experiment. And we want to observe is the intermittent interference. And for intermittent interference, the wave path will be integer multiple of the wavelength. And when it mated with white light, it will form a rainbow fringe, because the lambda of white light is from 400 to 700 nano, and the lambda of green light is 495 to 570 nano. And because that white light is a magnetic cloud. And this is a grating equation we use to calculate our theoretical value. And for the grating equation, it's talking about the wavelength differences. We use d sine theta to minus d sine I. It will be an integer multiple of the lambda. And d is the distance between groups, and m is a certain level of the diffraction, and lambda is the wavelength. And these are our experiment device. We cover black paper in the dark room to prevent the reflected from interfering of our incidence light, and it won't cause a lot of error.
By the way, you will take off your mask.
Oh, sorry. And this is a tripod we use to control our height and position of our light. And this predicts is we use to do our experiment. And this is the formula we choose to calculate our theoretical value. It's similar to grating equation, but the difference is we put our observation point and our incidence point on the same side. And in the grating equation, there is a great distance. It's m, and when m is smaller than 3, or it is free, we can see the green line because our diffraction will be blocked by the white light. And after acting the actual color, it will be like this picture. And as we can see in this picture, when the value is m, we can only see a little diffraction, and it won't be a green line, or maybe it will be like a green dot. And in the value of n, it will bring a clear green line. And in this picture, if our n value is bigger than 5, and we can see the diffraction because the angle will be larger than 180. And this is the great distance of DVD. And for DVD, BD, and CD, it isn't the same. It's because their groove pitch isn't the same. And this is the great distance of BD. And we assume this is a whole grating, and we can observe that the colored area is a grating area. So by observing from different locations, we can see different colors, and it is based on different distance between incidence and grating. And this is the formula we choose to calculate our theta r and theta I. And this formula is not derived by grating equation. It is just to calculate our angle angle theta theta. And we'll calculate our value x1, x2, y1, y2 in our experiment. And for our experiment, our independent variables first is about the diffraction material, CD, DVD, and BD. And the difference between them is their groove pitch. And for CD's groove pitch is 1.6 nm, and DVD is 0.74 nm, and BD is 0.32 nm. And the second is the end-level diffraction. And the end-level diffraction is relative to the groove pitch. And the last is the different incidence angle of theta I. And our dependent variable is the value of theta r. And this is the data of our CDs. And when we calculate our experimental value, we can see that the whole green line is from the front to the back. So we'll all both calculate about it. And in our experiment, we'll take a photo for the CD's green line, and we will put in image J to see the lambda of it. And for the front edge is 495. And this is a formula we use to calculate our theoretical value. And we put our sin theta and sin theta back to this formula so we can get the slope and intercept. And the intercept is m lambda divided by d. And we can see that their trend is the same, but their error is from their intercept. And this is the back edge of CD. And for CD, we just mentioned about that we can see the greatest distance of 4 and 5. And for 4, we also did an experiment about it. And this is the data of the greatest distance of 4 of the front edge. And this is about the back edge. And this is the data of DVD. And for DVD, the great distance is 2. So we can't see the whole total green line. We can only see half of it. So of the back edge of it, we only calculate a half of it. And this is the data of DVD's front edge. And this is the data of back edge. And for BD, the great distance is 1, and it's even smaller. So it is a little bit hard to observe. And this is the front edge data, and this is back edge data. And for discussion, we know that our error is at our intercept, and intercept is m lambda divided by d. But m and lambda won't be error because we already see the lambda in image J. So we calculate our d again, and after we calculate it, when the greatest distance is about 5, the d must be 1.5, but not 1.6 that we search on the internet. So we do the correction again, and this is the greatest. This is the greatest distance of 5, and this is before correction, and this is after correction. And after our correction, we saw that when the great distance value is 4, the groove pitch is about 1.45. And we also do the calculation of groove pitch of DVD and BD. But after our calculation, we saw that it doesn't have a big error, so it's very similar. So we didn't do a big correction. And this is the data of BD. And this is the error of our intercept. And we can see that the error of front edge is bigger than back edge because the back edge is more converse to our large angle. And this is our conclusion. First is that green line can be observed in large angles. And when the disk is illuminated with small angles of incidence, we can only see a green point, a straight green line. And second is we can know from the theoretical theoretical formula that the incidence angle and the observation angle are negative related. And the third is for great distance of CD, we choose the level 4 or 5 for observation because the green line we want to observe because the green line we want to observe will be covered by white light during the 1, 2, 3 level diffraction. And for great distance of DVD, we choose level 2 to observation because the green line we want to observe will be covered by white light during the first level diffraction. And for great distance of BD, we choose level 1 for observation because level 2 cannot be observed. It's already bigger than 180. Okay, I'm finished.
Okay. So on the opponent, you have 2 minutes to question the reporter.
Okay, so you illuminate the CD from different angles. From 60 to 80?
60 to 85.
60 to 85. And why did you illuminate the CD to 90?
Why
Just direct. You said it. Yeah.
I do this is because I use this to find the great distance.
What?
I use it to find the great distance in the groove pitch. For if I illuminate it by a large angle, it will be a bigger arrow. So if I illuminate it in 0, it will be little arrow. The arrow will be smaller.
Oh.
And this is only for I use.
Okay. So can you get back to what do you mean the sine theta? Can you get back to the formula? And what does the mean distance between groups? And how do you calculate the groups? The distance between the groups?
I use green laser pointer to illuminate the disc, and it will have 1, 2, 3, 4, 5 great distance. And I put the data in gradient equation so I can get the value of D.
Okay. And have you used different types of light to illuminate the CD or DVD?
We only try to use white light or another, maybe green light or white light. Green light or red.
Different colors of light?
Yes, different colors.
Oh. And what type of light source did you use?
I use
Okay, time is up.
Okay.
So you have 3 minutes to prepare.
I'm ready.
Okay. So the corner you have the first 4 minutes,
4 minutes.
up to 4 minutes, and then followed by the discussion with the reporter.
Okay.
And if you like, you can take off your mask.
Oh. Alright, and on an opposition on problem 4, color line, this is equation in T-narrow. Here's the problem statement. It says when a compact disc or DVD is illuminated with light coming from a filament lamp in such a way the only rays with large angles of incidence are selected, a clear green line can be observed. The color varies upon slightly changing the angle of the disc, and they explain and investigate this phenomenon. Here's the structure of solving the problem. They first design their experimental device and they experiment with different angles to illuminate the CD or DVD and discuss about the data. Here's the report. They have their theoretical model via literature. They have simple, understandable, qualitative explanation of the problem and appropriate use of media. They take several videos to show us different slides from CD and DVD. However, they lack explanation of why the phenomenon appears and the missing investigation of different light sources. And when it comes to experiments, they have a clear, accurate, and reproducible setup and sufficient investigate of the results. And they have comparison of different angles to illuminate the different CDs. And however, they have the parameter. They don't measure different light sources. The theory. They have relevant modeling of how to calculate the lambda. They use the formula to show us it. And however, they have unclear how modification of theory was actually done, such like insufficient model of the phenomenon, which means they only show us the results, and I can't totally understand why this phenomenon appears. So in the next 10 minutes, first I want to discuss with them is how the phenomenon appears. And the second is that is there any other variable that will influence the phenomenon, such as from different distances to illuminate the CD or DVD. And I also wonder if we observe it from different angles, will it be a light or it will be an area on the CD or DVD? This is all I want to discuss in the next 10 minutes.
Okay, start the discussion.
So, as we just mentioned, we just use one type of light, right?
Right.
Okay. And can you show me again how different color influence the results?
This one? Hey, how? Sorry, can you say it again?
Okay. You use different lights, so will it have different results, or they just all the same?
The diffractions, the color of diffraction won't be the same. If I use green light to illuminate it, it will be a green diffraction. It will be a green light. If I use red one, it will be red. But if I use white, it could be a lot of color because white light is a specific light.
Okay. And Have you discussed how this phenomenon, why will this phenomenon appear?
Because when white light hit the grating, it will have wavepath differences, and wavepath differences will cause its diffraction color isn't the same way illuminated by white light.
In my opinion, was it because of interference? That means if you illuminate the CD and use the effect groups, right? And if it will get to different angles, and you will have constructive interference and destructive interference. In my opinion, what do you think?
Yes, I agree.
Okay, and then perhaps in this way, then different types of colored light will appear, since they have different lambda.
Yes.
Okay, so this is my opinion. Do you agree with me, or you can?
I agree with you.
Okay, so we should investigate how the green light is observed. Okay. And have you tried to illuminate the CD from different distances?
Different distance, but I think that the important place is its angle, isn't the distance. The farther distance it won't matter a lot, I think. We have tried before, but it doesn't matter a lot.
I mean, if you illuminate it farther, and it would be the light source will be close to a parallel light, like sunlight.
Yes.
And so that would have little influence to the result of the experiment.
We think that we tried before, but we think that it doesn't matter about, because when it is farther and it make it in a parallel light, it will just be that the green light won't be so clear. So we didn't put the experiment here.
And you just mentioned BT. Can you explain it more clearly to me?
BT is a disc that, when it is coding its data, it uses blue rays to code its data. It's another kind of CD, but
okay,
it's
so
distance.
So you mean the groups are different?
Yes.
Oh, okay. And will this phenomenon be also related to diffraction? I'm not sure. I'm just asking.
But sorry, can you repeat it again?
Okay, that's fine. And so, have you observed the light from different angles?
Yes, we tried before, but we tried in small angles. But when it is in a large angle, it won't. I can only see a short green line, not the whole clear green line.
No, I mean you observe the green light from different angles. If you can observe the green light in this, and if you look at it on the other side,
it will be another color.
It will be another color.
You mean up and down, or if you try it?
You keep the device at the same place, and you observe it from different sides.
Different sides. We didn't try it.
Oh, okay. So can you give me your data again? So you get this data from that We get this data from the formula.
For theoretical data, we get it from this formula. But for our experiment data, we get it from we do the experiment.
Oh, okay. Can you explain this to me again?
For our experiment data, we get theta r and theta I, so we know the value of sin theta r and sin theta I. So we know the n value when we are doing the experiment, and we know the lambda in our experiment when we put the picture in image J, so we can get D, and for theoretical value we know sin theta I and n lambda divided by D, this value, so we calculate the sin theta r.
So do this chart just mainly discuss about the sin theta r?
And sin theta I. But for this data, we want to tell is that our theoretical data and experiment data is on the same trend.
Okay. Can I use the board?
Yeah, sure.
You say the light just illuminate light and the CD has groups. So it should be something like this, CD. So where does the light illuminate? Like it gets in here or here?
In our opinion, there is two reasons that it has wavepath differences. One is intermittent in here, and my screen is here. And for here to here, it isn't the same distance. So it will have first wavepath differences. And the second is from here up to here and up to here. We will have the second wavepath differences.
Oh, so perhaps this can also explain why this phenomenon exists. So it would have different light if you see it. And perhaps then different colors will be observed. Right? In my opinion, I'm not sure. Or are they all the same colors?
These two will occur at the same time. So these two occur at the same time, so it will produce that green line.
Okay. And you mean DVD has more proofs than CD?
More proofs.
The proofs are closer.
Yes.
So what would
Like maybe CD is like this.
I mean the results.
The results. It's
Can you show me?
It's result. It is designed like this. DVDs, the group pitch of DVD is smaller. It is designed like this because the data they can put it in is more.
So if that's the proof and the angle, if you have more proof, do you need the angles you needed to?
No, it doesn't matter.
It doesn't matter.
It only
Okay,
matters
time
about
is
this
up.
resistance.
So the comment, you have 1 minute to summarize your discussion with the reporter.
Okay. First, we talked about a lot of things, and first we talked we talk about that the grooves, the close of the grooves and the sine theta will have any influence, and the reporter says no according to their experiment, and we also talk about the phenomenon, and we get the answer is perhaps, in my opinion, it is close to it can be explained by interference, which and we also talk about different sources of light, and they haven't done it, but they use different colors of light to do the experiment. And
Okay, the time is up.
okay.
And the reviewer, you have 3 minutes to raise your question.
Okay, so the first question, we're going to talk about the problem statement. So the problem statement asks us to have a large angle. So how to define a large angle?
We try to use green laser pointer to eliminate the this. And
how about the opponent things? The large angle to be defined.
Oh, that's quite interesting. Perhaps I think we can define large angle. So if I'm doing an experiment, I'll use all the angles from 0 to 90.
Okay, I got it. So about the problem statement, it also mentioned the DVD and the CD. So what's the differences between these two? Kind of this.
their groove pitch isn't the same.
And how about the opponent?
Oh, and the DVD's groove are closer and the CD.
Okay, I got it. And now let's move on to the theory part. So can you briefly introduce why there's only one line up here? One single line.
Because I can explain.
Okay, how about the opponent?
I'm not sure. Perhaps there may be many different lights, but we just observe the green light.
Okay, so can you briefly answer why CD is able to seen as a diffraction grating?
Because it has.
Okay, how about the opponent? Do you agree with the reporter or?
Repeat.
Can you briefly answer why CD is able to be seen as a diffraction grating?
I agree with the.
Okay, so since we know that light is a kind of electromagnetic wave, so did you consider magnetic field?
No.
And how about the opponent? Do you think it has to be taken into consideration? The magnetic field.
The magnetic field.
Yes, because we know that the light is a electromagnetic wave.
Perhaps, but it will just have little influence to the result.
Okay, and how about the electronic field? Do you think it have to take into consideration?
What is an electronic field?
Well, how about the opponent? Okay, so now let's move on to the experiment part. Okay, let's just use this graph. So do you think there should be 2r squared in the same chart? Yes, there's 2r squared. Do you think it should be 2r squared in the same chart? Because it's a big one.
But it is just used to say their trend is the same.
Okay, how about opponent?
I don't quite understand what it is.
If they're able to have 2r squared in the same chart.
I'm not sure because I don't quite understand.
Okay, so what do you think is the main reason there have a distance between these two slopes?
Theoretical and experimental.
What is the reason is the distance between them?
Okay, the time is up. Yeah, so the review have 2 minutes to prepare. Okay. You ready?
Yes.
Okay.
Let's move on. So thank you for the reporter and opponent. I'm the reviewer of this session, and I'm going to review question number 4, color line. And here's the problem statement. We main focus on the filament length and the green line and the color values. And the textbook field is partly fulfilled. And here's a summary of the reporter's presentation. So they main focus on observe the range of the green line, and also their theory use the interference and the diffraction grading. And for their setup part, they use 3 kinds of disks: the camera, the image J to analyze their data, and also the light sources. About the parameters, they use different disks and different angle that I think is pretty good. And the conclusion part, they mentioned that green light can be observed in large angle and great distance of BD. The LEGO 2 can be observed, and the great distance of DD, the green light will be covered by white light. And here's the pros and cons of the reporter. The pros is that she clear understanding of the theory and good experimental data analysis, and has own opinion, and also various experimental parameters about 3 kinds of disks and various angles. About the cons is that it's not clear understanding of the problem statement because the large angle part, and also lack of quantitatively theory and experiments. They may have a numberly data. And here's the pros and cons of the opponent. Opponent has his own opinion and accurately understand the reporter's presentation and some interesting discussion question. And for the cons is that it is not clearly understand of the problem statement too. And however, and some theory didn't understand detail. And here's the discussion point of the reporter and the opponent. The opponent asks why illuminate to 90 degrees, and the reporter answers that find the great distance and the pitch. And the reviewer agree with the measurement of the reporter to get the detailed explanation of its theory. And here's the next discussion point about the opponent asks about how the phenomenon appears, and the reporter answers that when the light hits the CD or DVD and even BD, the diffraction would happen, and the reviewer thinks that it would be the interference. And here's another discussion point. The opponent asks about if you observe the light in different locations but the angle not change, why did it happen? And the reporter answers that they didn't do the experiment. However, the reviewer thinks it would change since the distance have changed. And here's the discussion, another discussion point. The opponent asks about how different colors influence the results, and the reporter answers that the color of the diffraction would be same. And the reviewer thinks that the structure of the disk would have the incident light, which would have the interfection and the interference. And here's some area of the improvement. The first one is the misunderstanding of the problem statement. The problem statement asks about the various color of the line. However, the reporter didn't do the light that is at the green line, and suggests to mention the reason of only one line appear, because I think the reporter and the opponent is not clearly understanding this part. And as the reviewer, I think it's because the structure of the disk passing the diameter will be periodic. And another suggestion for the reporter and the opponent is that suggest to mention the reason why CD can be seen as a diffraction grading. And in the reviewer's opinion, since all of the checks on CD can be seen as a radiator, so when the lights are incident on the CD, these waves can be interference each other. So here's the end of my presentation, and thanks for the reporter and opponent.
Okay, the time is up. So the reporter, you have 2 minutes to make your concluding remark.
We think that first is that we didn't really know about the problem statement, and we didn't do the experiment for the color, the various color about the line. And the second is the location, but the same angle. And we didn't really know that the theory of why there is only a line on the diffraction. And we didn't try the different type of light. So maybe we can try using coral lights next time. And I'm finished.
Okay. So now it's time for the jury to ask you a question.
About the light source. In order for different colors to appear at different diffraction angles, isn't it necessary to have a white light?
We have tried before and we saw a white light, but we guessed that it is because we have a round experiments. Because we think that maybe it should only be a little white light.
But it's a white light.
Yes.
That is full spectrum of colors, right?
Yes.
White light has a spectrum containing 7 different colors, so with different wavelengths. Okay.
Okay, so the reviewer believes that if the light contains the green line, the spectrum, it can be observed the green line, and
But not when it's white.
Hmm?
When the source is white,
yeah.
can you observe green light as well as other green color as well as other colors? That's my question. Okay, maybe.
I believe that in different angles, different colors can appear in.
Okay,
yes.
thank you. That
So-
seems to be your concern.
So you mean if you manipulate the white light, would it appear many different other colors?
You ask, you report changing the light source,
The light source,
the light,
the light. You just
instant light.
instant light.
Isn't that what you want? You want the reporters to?
But you just say white light and
Yeah, I'm just asking you why changing light? If all you need, maybe it's just white light.
oh, what if you use razor?
Excuse me?
If you use razor, what would it happen? I'm not sure.
Razor?
Razor, yeah,
Laser.
laser,
Oh, you mean laser?
laser. I'm not sure.
But laser, if it's just one wavelength, you always see the same wavelength.
And from different angles.
Your refraction doesn't
Okay,
change
okay.
wavelength,
Okay.
any diffraction. Okay.
Okay. Any other questions?
Maybe just to reporters, so so in your analysis, the number of M already determined. Is that right?
Sorry.
So the value of M is input. You already know it.
I already know it.
So why is that?
I use screen laser pointer to illuminate this, and it will have 1, 2, 3, 4, 5 diffraction. So I draw the point that the point that
Okay,
is
got it.
diffraction.
Okay. To the reviewer.
I agree with the calculation method with the reporter. I think it's reasonable
Yeah,
method.
this is not the question.
Sorry. Sorry.
So how do you think the large angle affects this? How do you think the large angle is crucial? Why is that?
Because in the problem statement, it mentioned we have to observe the green light in a large angle. So I would like to know.
Probably my revert my question. Why the large angle is crucial for the green light? Any short explanation or what?
It is related to the wavelength of the green line. So it should be a large angle, I think. Yeah.
You have question to the opponent? No?
No, specifically.
Okay. Okay, so that's it. So let's prepare the scoring. Okay, so I think it's time for the jury to show the scores. So for the reporter, okay, so it's 76556. Okay, then now let's show the score for the opponent. 56657. And finally, let's show the score for the reviewer. 78988. Okay, so we have another 10 minutes break. And start the last stage of phase 5. So please have your seat. Please sit down. Okay, please sit down. Okay, the opponent, you have 1 minute to challenge the reporter. So the 1 minute is almost up. Okay. You have your questions ready?
We would like to challenge problem number 15, pancake rotation.
Okay, so problem number 15 is a static. And the reporter, you have 5 minutes to prepare. And the reporter, when you are presenting your speech, please take off your mask. And could you please write down the name of the representative? Okay, time is up. The reporter, you have 12 minutes. Good.
Okay, today I'm going to present number 15 problem, PF1 quotation. Place a few balls in a round container. If we move the container along a vertical axis, the balls can move co-directionally with the movement of the container, or they can move in the outside direction. Explain this phenomenon and investigate how the direction and the movement depends on relevant parameters. And this is my experiment observation. And in this observation, we can observe that the ball have control location in high quality, and we can also observe that the ball have a spatial check. And this is my experiment device. The radius of particle is 2 centimeters and weight of particle is 2.5 grams. And the radius of the container is 10 centimeters and the amplitude of rotation is 4 cm. And we also use tracker to check the check of the particles and side debris to analyze our experiment data. And after the experiment observation, I find some interesting phenomena in this video. And first, why the particle have different movement in high quantity. And second, will particle have different movement in different surface of the particles. Third, will particle have different movement in different velocity of container, and that's how friction affect movement of particles. And now I'm going to analyze why the particles have constant rotation in a component. And this is step 1. When we just turn on the rotation base, the particle will have the same velocity as the container because there is static friction between the particles and the container's bottom. And second, when the container change its velocity, the particle will also change its routine because the red line is the origin routine the particle has, but there is friction between the particles and the bottom of container, so that the routine of the particle will bend. And step 3, when the particle collision the wall, the particle will rebound and its routine will also bending because of the friction between the particles and the bottom of the container. And step 4, when two particle collisions, they will have the outside rotate because there are friction between them. So after this analysis, we found that at low quantity, the particles at the wall in the pin region are free to spin and roll locally, and falling behind the moving wall and effectively reduce the particle cross friction and reaction with the container and other particles. And after, if we decrease the step 1 to step 4, we can draw this photo, and this photo is the track of the particles. And we can find that the container moves around a vertical axis, so the particle will rotate. Then the particle will rebound when it collision with other particles, so we can observe that the particles track just like a spiral or a spring. And when interparticle friction is strong between two contacting particles, they must spin about their own axis in outside direction, and later we will use the experiment to prove it. And now I have 4 research purposes. And first, how do the particle quantity affect the movement of the balls? And second, how do the surface of particle affect the movement of the balls? Third, how do the velocity of container affect the movement of the force, and last, how do friction affect the movement of the particles. Okay, this is my first experiment variable. I'm going to research how the quantity affect the movement of the ball. And this is my formula. I use this formula to calculate the average angular velocity, and I will make it to a graph. And this is the x central of mass, and this is the y central of mass. And this is my experiment result. We can the vertical axis is the average omega, and the horizontal axis is the particle quantity. And we can observe that when the particle is in the extreme, the average omega will just like a linear. And my experiment result is that when during 2 to 0 particles, the particle rotates the center as the container, and when during 8 to 10 particles, they have an velocity movement in the container. And during 11 to 15 particles, the particle rotates outside as the container, because when it has enough particles, they will hit and rebound, and then cause counter rotation. And this is my second experiment variable. Here I'm going to research the particle surface. And this is my experiment result. We can observe that when the particle quantity is in an extreme, they will also have a linear. And the vertical axis is the average omega, and the horizontal axis is the particle quantity. And my experiment result is that when the particle become concentration at the raw particle earlier, because the raw surface will cause strong friction, and when the two balls collisions, or the balls collisions with the wall, they will also have the strong rotation in this phenomenon. And this is my second variable. I'm going to research the velocity of container. And here I use two kinds of velocity to research these items, and the data will is just like linear, and the condition is that they need to in extreme. And my experiment result is that when the velocity of the container is increased, the acceleration of particle will also increase. And by this formula, when the acceleration increases, the force between wall and the particles will also increase. And this simulation is experiment, and in this experiment, I will research why the friction will affect the movement of the particle. And here, when this is there are friction on the surface, we can see that the particles movement and rotation. And in this video, there are not any friction between the particles and surface. So, and we can observe that the particle can rebound on the surface, and we cannot move to other places. And after this experiment, we observe when the interparticle friction is strong between two contacting particles, they must be about their own axis in outside direction. This is my conclusion. And in my experiment, the condition of the experiment is that there are a variable area of ratios, and the ratio is between 3 divided 25 and 13 divided 25. And when the H and after the first increment, we find out when the H omega is bigger than 0, the pi corresponds directionally with the movement of the container, and when it's smaller than 0, the pi moves outside direction in the container, and when it's near the 0, the pi cores still square and slide, but they don't have a velocity movement. And after the simulation experiment, we find that friction is an important point that will greatly affect the pi cores movement. When the surface is more rougher, the pi cores will change to counter rotation earlier. It's just like the second experiment. And when the friction of container is 0, the rotation will affect the movement of the pi core used like the simulation experiment. And when the pi core friction is stronger, the pi core have more square in their movement, and when the pi core friction is smaller, the pi core have more slide in their movement. And this is my end of my presentation. Thank you for watching.
Okay, so the opponent, you have 2 minutes to question the reporter.
Okay, please turn to page 4.
Page 4.
Does the amplitude mean the angular velocity or the radius of the rotation?
The rotation basically it will shape and is amplitude mean how like the rotation base shape.
Okay, and could you turn to page 7, please? So the friction here is the static friction.
Yes.
Is that correct?
Yes.
And so turn to page 8. So may I ask that you say you change the velocity, you change the direction, or you change the volume of the velocity?
Yes. Here the velocity of container means because the container will shake, so it's just at a different term.
So you say the container will shake.
Yes.
Okay, and please turn to page 10. So so the velocity here is the tangential velocity for the particles.
You means the this or this?
The upper.
Yes.
The velocity.
Oh yeah. No, it's just like it's routine. It's the routine.
Okay, please turn to page 14. Does the trajectory that you draw is considered a single particle or variable?
Thumbs up.
It's just the
Thumbs up. Okay, so the opponent, you have 2 minutes to prepare. Okay, so before the discussion, the opponent have up to 4 minutes to comment.
Thanks for the reporter, and I'm the opponent from Team Epsilon for concluding problem number 15, pancake rotation. And first we can look at the problem statement. It's mentioned that we need to have the container should be around the vertical axis, so the container should have the rotations, and both can move co-directionally with and the opposite direction, and it depends on the other parameters. And here's a summary about the reporter. First, as a theory, they mentioned about the friction effect and the collision effect. And in their opinion, they think that if the friction equals to 0, that the effect will become to 0 about the co-directional. And for the experiment, as a setup, they use a ping pong ball for the particles that they use, and they use a motor to control the rotation is stable. I think this is a great experimental setup. And as a parameters, they change the amount of the particles, volume of the particles, and different friction about the particles and different velocity. I think it matches the problem statement that tries the relevant parameters. And about the method, they use tracker for analyze the trajectory of the trajectory and the angular velocity about the particles. So the conclusion, the conditions about the phenomena is area ratio, and the angular velocities will decide the direction of the rotation. And the friction is an important factor for the for their results, since they say that when they assume the friction is 0, the co-direction won't affect. And when surface is rougher, the direction will change into the opposite side. And here's the strength and the area for improvement about the reporter. I think they have completely qualitative phenomenon explanation about the reason why the particles will move in the different directions. And they have a lot of experiments to prove the assumption that they just mentioned. And about the assumption, they have the great assumption and use a simulation to assume that in some conditions, they will have the boundary about the rotation. And they have the good experimental setup, such as they use a motor to make the rotation stable. And they found the boundary of different movement depends on the ratio of the volume of the container and the particles. And about the area for improvement, I believe that the reporter have a lack of quantitative comparison between theory explanation and the experiment, since they have provided formula to calculate the omega 0, and they have lacked explanation for the experimental results. And for they did not explain the effect of the collision well and analyze the method didn't show, like how do they define the angle and the angular velocity. An unclear physics picture and a simple explanation of the phenomena, and could measure the friction and coefficient in the system would be great, and too ideal to assume that the friction is zero in their cases. So I think the test problem for this problem, I will say it is a positive problem. And then I thank for your listening, and I would like to move on our discussion. Okay. Could you turn the page about your problem statement?
Here.
Yes, for problem statement, it says that the container should move around the vertical axis. How did you define your vertical axis in your experiment?
Here the vertical axis is, because in the container you haven't said where is the vertical axis, so I set this vertical axis on the wall, the container's wall.
And which point? So your experimental setup that you move along the container's wall in a single point for the vertical axis.
Sorry, can you repeat it?
The question that I want to ask is, how do you define your vertical axis in your problem?
Oh.
Maybe we can use the board.
Oh, yeah.
It seems you want to provide rotation containers on the vertical axis. There's a lot of points that you can define. First, it's the middle, it's like you said, it's the wall of the container. It's one of the possible that you define the vertical axis. Another is everywhere in the container you can define it as the vertical axis. And the vertical axis will define the radius of your rotation of the plate. So where did you define your vertical axis?
I just use a point and this is the routine that this point will work.
So you define a point on the walls on the container, and you make it rotate about this volume.
Yes.
So how does the radius of your rotation?
Yeah, that is about
Radius
2 centimeters.
2 centimeters. So the 2 centimeters is your radius of the rotation. 4 centimeters. And I would like to ask, why do you define it as an amplitude? Like you said, it was shaking, but you said you now say it is in a rotation.
Yes, the shaking I mean just this.
Okay. And move on to the next question about the problem statement. Do you done the experiment for the directionally for the movement of the ball?
Sorry, I don't forget.
Okay. In your experiment, does your ball move along in the same direction with your container?
Yes.
Yes. And do you done the experiment that have the opposite direction?
Yes.
And so, which conditions will make the balls move along with the same direction with the plate?
When the quantity of the particle is small, is low, and they will have the same direction as the container.
Okay, let's move on page 7. Does the particle have their independent movement on the plate?
Independent movement.
Let's ask the question again. That have the relative velocity with the container.
Because it just does so, now it have a.
Okay, so the direction of the velocity, since you have say that the setup that you use is a rotation, so why don't you consider? So what is the velocity is your parameters in your problem in this problem? What is the velocity in the problem? Does the rotation need to change your velocity into an angular velocity? No. How do you think?
Here this This just means a moment. Yes.
Okay. So please turn to page 10. Okay. So you say that the two particles will have the interact with each other. So do you think the collision is the main reason that you have explained?
Not at all, because they didn't have collision and they will touch, and so they will
Make the friction.
Yes.
So where's the direction of the friction between the two particles?
So can you repeat?
Which direction is the friction between the two particles?
Because this ball rotation is clockwise, and when the
Yes, I'm asking. Sorry, I'm wondering about the collision that you say the two balls will collision. Is that correct?
yes,
And they will provide a friction.
yes.
As you work. Then where is the direction of the two particles between the two particles?
They will have the outside when this the purple line is their rotation.
I'm asking about the friction between the two particles. Is the same side with the container or a different side with the container?
Or the ball just collision with the wall will outside as the container, and this.
So do you think there's really a friction between the two particles? If there is a friction between the two particles, there should be the direction of the force. Maybe move on. So in my opinion, I think the rotation is a different direction. So I think the friction will be the opposite side with the velocity of the container. So could you move on page 17? 17. Oh. Could you explain the formula here?
Well, here we use this formula, and this formula can calculate all the particles in the
So
container.
could you tell me where's the differences between the omega and omega I?
The omega I is a function. Yes, and the omega is the angular velocity.
So here you calculated the average angular velocity with the particles.
Yes.
All the four particles. You calculated the average about the four particles or the single particle.
All of them.
So you think that all particles have the same direction of
No.
So if the particles differences size will affect the result, is there any parameters that will change in the angular velocity that if you change the differences size for the particles?
Because we don't have used the different size of particles, so I can check.
I'm asking about the formula. Does the formula has any any terms that you can change the particle size? Or in my opinion, the reporter says that the volume between the ratio of the volume of the container and the balls will change the direction of the movement. Is that correct? So I think maybe the formula here just can calculate it in some certain situations, not the situation that the problem statement mentioned.
No.
Could you explain why?
Sorry, I can't.
Okay, let's move on to page 21. Do you measure the friction between a smooth surface and a rough surface?
You need what? You need the difference.
Friction coefficient.
Yeah.
Can you measure?
No, I just know one is smooth and one is rough.
And I would like to ask, after the fourth quantity over the 14, there is some data will increase. Could you explain why?
No, this is an interest phenomenon in this experiment, but I can't explain because in my experience.
I think maybe that is because the amount of the particles increase, that makes the collection of the in your container has decreased, which means the velocity will also decrease. So the collection effect won't barely to be observed.
Yes.
Is that possible?
Maybe.
Okay, could you turn the page about 25? You calculate A equals to NA, so what's the force you are calculating?
The force is that when the ball collisions with the wall or the particles collisions particles.
But why will the acceleration appear in your setup, since that your setup has the same velocity, is that correct?
Yeah.
So why is there will be acceleration?
Okay, time's up.
Okay.
Okay, the opponent, you have 1 minute to summarize the discussion.
Thank you for answering the question for the reporters. And first is we discussed about the amplitude, that the reporter says that the amplitude is the radius of the rotation about the container. And then we asked about the static friction between the container and the bolts. And between the bolts and they have the parameters, things that they change the friction between the bolts and bolts, but they didn't measure the friction coefficient of in these parameters. And about the data that they provided, when the amount of the particles have been over the 14 particles, that the data will increase. In my opinion, I think it's caused by the collision. When the amount of the particles have increased, the collision won't have happened fairly as the other situations. So about the experimental setup, they say that their setup has the same velocity, but here they talk about the acceleration about the system.
Okay. So the reviewer, you have 3 minutes question.
How to avoid the effect of the rotation? How to avoid the effect of the rotation? Can you briefly explain the phenomenon?
It means the concentration of the. It means the concentration of the particles. Yes. Here we analyze the why the particle has counter rotation, and here we just turn on the rotation phase. The particle will have the same velocity as the container because it has static friction between particles and container, and then when the container change its velocity, the particles still have inertia, but they also have friction between the container, bottom of the container and particles, so the routine of the particle will bending. And then when it collisions on the wall of the container, it will rebound and it will change its routine again.
Okay. Which kind of force do you think affects the most?
I think the friction.
Friction, and how about you?
I think the friction and the collision between the two particles.
Can you turn to page 10? balls will not touch together.
Will touch together.
Okay, I'll just turn to page 31. Okay, where do you get the two numbers?
Two numbers, we use this is the here.
Time is up, and reviewer, you have 2 minutes to prepare your comment. Okay, the time is up, and reviewer, you have 4 minutes to comment.
Okay, I'm going to review the pancake rotation. Problem statements. Place a few balls in a round container. If you move the container around a vertical axis, the balls can move co-directionally with the movement of the container, or they can move in the opposite direction. Explain this phenomenon and investigate how the direction of movement depends on relevant parameters. And the advantage of a reporter are fair explanation of phenomena, and observation video, and well-structured presentation. And further suggest, I think you need to explain more from formula or the theory, and know more about the theory and formula. And for the opponent, their advantage, good imposing manner, and find out detailed mistakes of the reporter, and ask thoughtful questions, and provided answer to their own questions. And suggestions is ask the question theory. And for the discussion, what is the change as static friction? And the answer is the velocity of container. The container will shake. And what is the velocity particle mention? Velocity particle is about routine. What can make your ball and container move the same direction? The velocity is slow. And thank you.
Okay. So finally, the stage in this stage that we have 2 minutes for the reporter to make concluding remarks.
Okay, and after the reviews and opponents' suggestion, I think I need to more understand what the opponent said and more quantitative of my experiment theories. And I also need to more understand the formula and need to explain why we use formula and some parameters of the formulas, and I need to explain more about the data than other can know my explain more.
Okay. So we have 5 minutes for the jury to ask questions.
I just want to clarify the definition of the rotation. So, for your particle, I think there are 2 angular velocities. So the particle moves, right, and the particle will spin from your video. So, are they always the same direction, or sometimes they are opposite? In such case, how do you define your angular velocity or your rotation?
No, sometimes they will change their side.
And the same question to opponent and reviewer. Then, what's your definition of the rotation in this scenario?
That the definitions about the rotation.
Because from the problem, you have to define the rotation, right?
The rotation of the plate
or the particle.
So I think the definitions about the rotation of the particle for the particle statement state may be the direction for the whole cluster of the particles.
Cluster of particles.
Yes, not the single particle.
I think the velocity is better than the direction will change.
Just one more short question. And most of you has focused on the case of ping pong ball, which friction dominated regime. How about the inertial dominated regime? Do you think inertia is a critical parameter that affects behavior? Inertial dominated regime, and it's a solid ball.
I think in my experiment, the surface of the ball and the mass of the ball will affect the rotation of the particles.
How about?
I think the parameters that the professor mentioned will affect the collision. What's that collision provide?
Collision?
Yes, it will change the collision, then it will change the direction of the rotation of the cluster of the force.
I think I agree with that.
Okay. Do we have any more questions? Okay, if not, let's prepare the scores for the 3 teams. let's show the score for the reported. Okay, the score are 56545. And then let's show the score for the opponent. Okay, the score are 77777. And finally, let's show the score for the reviewer. 67754. Okay, thank you for all of your participation. And that's end this stage of the physical 5. So, do you have anything to announce? No? Okay. So, this is my